In this section, I will introduce about the PN junction diode. Before we learn, we can know that there is a band-shaped structure of N-type semiconductor and P-type semiconductor, and there is a specific quantity of Fermi level energy of N-type semiconductor and P-type semiconductor, and there is also the same quantity of the energy band gap of each type of semiconductor. However, we can think that there is an uh, uh, we can categorize we can divide each Fermi level energy to the Fermi level energy of the N-type semiconductor and the Fermi level energy of the P-type semiconductor. And so we can find some specific characteristics, which is that when we make the difference of the vacuum level energy to the each Fermi level energy of which is at the Fermi level energy of N-type semiconductor or Fermi level energy of P-type semiconductor, we can find that the work function of each type of semiconductor, which is expressed by the difference of the vacuum level energy to the Fermi level energy, and thus we can find the different quantity of the work function of each type of semiconductor. And also here, because I didn't say before, so here is the same level of intrinsic Fermi level. When there is undoped. However, when we look this band shape of each type together, there is a non-equilibrium state. So to make the thermal equilibrium, here is in non-thermal equilibrium state. So to make the thermal equilibrium state, we can make the Fermi level energy of each type of semiconductor in the same level, so we can make that downward to make the band shape of the N-type semiconductor downward, so and illustrate the band shape like this. So for here, the middle side of the band shape is curved like this, and as a result, we can make the Fermi level energy of each type of semiconductor in the same level. And also for the intrinsic Fermi level is because there is the same level of intrinsic Fermi level before, so it is also sort like the band shape, conduction band and the valence band shape. So yes, and also the vacuum level energy of each type of semiconductor is also squared. And for this quantity of this curved shape, we can define this quantity as the built-in potential energy barrier, which can be expressed like charge quantity multiplied by the built-in potential. So this quantity is from the calculation of the difference of the work function of p-type semiconductor to the work function of the n-type semiconductor. And here, as we learned before, in the n-type semiconductor, there is a donor which is ionized to the plus sign, and here p-type semiconductor, there is an acceptor which is ionized by the minus sign. So here, this donor and acceptor is the fixed charge. So when we can find that there is a local plus sign in the n-type semiconductor and the local minus sign in the p-type semiconductor, and here we can make the result of that there is an intrinsic E field from the n-type semiconductor to the p-type semiconductor. And when we apply the voltage, which can overcome this intrinsic E field, this can be named as the forward bias, which is that the potential built-in potential energy barrier is lowered as before. So there is the high possibility of the electron, which is that the electrons can overcome the barrier. So the current can be flew by this forward bias, and also there is yes, this by overcoming this the potential energy barrier, there can be the current flow, and reversely, when we apply the negative bias, which can make the potential energy barrier high as before, there is the low possibility of the electrons which can overcome the barriers. So their current flow can be can't exist as we compare to the forward bias. Thank you.